Now the log normal distribution we saw had a long right tail. So this gives rise to the notion of some distributions are not symmetric about the mean value. So when we talk about shape characteristics of a probability distribution, the shape characteristic that measures the symmetry of a distribution is called skewness. Now, skewness is based upon taking a function of a random variable where the function is the random variable minus the mean divided by the standard deviation, all of that cubed. All right? And then the skewness is the expectation of g of x. It's the expected cubed deviation from the mean standardized by the standard deviation. Right? So why is this measuring skewness? Now, if x is way above the mean, then x minus the mean is a positive number. And when you cube that, you're going to get a big positive number. Right? So if most of the values of x, in some sense, are above the mean, then when you take the expectation, when you take the probability weighted average of this, then you're going to have mostly positive numbers. Right? So you would have a positive skewness if there is a tilt in the distribution to large values. Okay? So that would be the case where if you had a distribution that kind of looked like this, whereas the mean of the distribution might be here, but we see that when you have values of x below the mean, right, they're not too large, but when you have values of x above the mean, you can get some really big ones. So when you're evaluating skewness, which is the probability weighted average of x minus the mean cubed multiplied by probability, or in a continuous random variable, we would take the integral weight by the density. In a distribution like this, these big numbers would dominate this calculation, and it would we'd get a positive number. So this is a situation where the skewness of x is greater than 0. And then we can think of a reverse situation. So if we had a distribution that kind of looked like this, so now say the mean of x is here, then in this distribution, we have a long left tail. So the values of x above the mean, they're not too far above the mean. So when you calculate x minus the mean cubed, you don't have such big numbers. But now when you look at values of x below the mean, there's some really big ones below the mean. So x minus mu of x is a big negative number. And then you cube it, and you make it an even bigger negative number. So when you have a distribution that looks like this, when you perform this calculation, these big negative numbers below the mean dominate, and you'll get a skewness that's negative. So this gives you the skewness of x that's less than 0. Okay? So right skewed data, this is called a long right tail. Left skewed data, long left tail. Then in a symmetric distribution, like the normal, if things are symmetric, then the values above the mean and the below the mean cancel out. And so when you calculate the skewness, you get something that's equal to 0. So in this case, we would have the skew of x equals 0 for symmetric distribution. So the example discrete data set was this one where we had the probability distribution for rate of return, and there were 5 states of the economy, and then we had probabilities associated with the states, and then return values for the states, and we have the discrete distribution look like this. So let's compute the skewness for this distribution. So what do you suppose the skewness is, just by looking at the distribution? Yeah, it's 0. This is a symmetric distribution. So when you calculate skewness, if there's any justice in the world, then you should get 0. So I like this phrase, if there's any justice in the world. As a stat professor, actually, I TA'd for a stat professor when I was in grad school. His name was Burton Singer. He used this phrase a lot when he was like deriving something and it looked like this really horrible calculation. He would say, if there's any justice in the world, it would simplify into something nice. And most of the time, that happened. So when we do this calculation here, so what is the skewness? And so we take the return value minus the mean cubed, weight by the probability, return minus the mean cubed times probability. You sum them all up, then you divide by the standard deviation cubed, and lo and behold, it is 0. Okay. Now, for a normal distribution, so if x has a normal distribution with mean mu of x and sigma x squared, then when you evaluate the skewness, you have to compute this integral. And and if you're good with calculus, then you can show that in fact this integral is 0. Now, on the other hand, if we have a log normal distribution, so we saw previously that the log normal distribution had a bit of a long right tail. So we would expect the skewness for a log normal to be positive. And in fact, if you do the calculus on the log normal distribution, you can show that the skewness of a log normal random variable actually has this analytic expression here, and this is positive. So the log normal distribution exhibits a long right tail. Now, another shape characteristic that's particularly of interest for us in finance is a shape characteristic that tells us about the likelihood of extreme values, right? So if we're looking at daily stock returns on the S&P 500, we know from time to time there's a market crash, and so when the market crash happens, we get a return that's in the far left tail of the distribution. And we can also get an extreme positive event. There could be a time when, for whatever reason, the market goes up by a huge amount in a given day. So, that's an extreme value on the right tail of the distribution. Okay. Now, when we start looking at asset return data, particularly if we look at daily data, the normal distribution fails in a big way. And one of the ways that the normal distribution fails is characterizing the likelihood of extreme events. The normal distribution doesn't imply that, the normal distribution implies that extreme events don't happen very often at all. But we see extreme events happening actually quite often. And so we would like to have distributions that imply a higher likelihood of extreme events than the normal distribution. And so we'll be looking at some of those kinds of distributions in this course. Now, how do we measure the likelihood of extreme events for a distribution? So one type of measure is known as kurtosis. And the kurtosis is based upon a function of the random variable. And the function of the random variable is the random variable minus the mean divided by the standard deviation raised to the power 4. Okay? Now, and then the kurtosis is then the expectation of this function. So it's the probability weighted average of the deviation of x from its mean standardized by the standard deviation raised to the power 4. Okay. So let's draw a picture here. And let's say we have a distribution that looks like this. And here's the mean. Okay. So first thing to note about kurtosis is that we're raising the deviation of x from the mean divided by the standard deviation to the 4th power, right? So this deviation is always a positive number, right? Now, if x is way out in the right tail, x minus the mean is a big number, right? And then when you standardize by the standard deviation, it's still a big number. You raise it to the power 4, you're going to get something that's huge, right? And the same thing is true on the other end. If x is way below the mean, then x minus the mean is a big negative number. Divide by the standard deviation, still a big negative number. Raise to the power 4, you get a big positive number. So the kurtosis accentuates the extreme values. So any distribution that has values that are way below the mean or way above the mean is going to produce a large value of the kurtosis. Okay? So extreme events, both positive and negative, lead to large kurtosis. Now, we compute the kurtosis by taking the probability weighted average of this deviation here, weighted by the probabilities if we have a discrete random variable, or we have to evaluate this integral if it's a continuous random variable. Right? So again, these calculations look a little bit horrible. If we do this calculation for our example data, so for a discrete distribution, how would we calculate kurtosis? We would take the return minus the mean, raised to the power 4, multiplied by the probability, add return minus the mean, raised to the power 4, multiplied by probability, sum them all up, and then divide by the standard deviation raised to the power 4. We get a number of 6.5. Okay. Now, when we calculate kurtosis, how do you know if 6.5 is big or small? Right? Compared to normal, exactly. So what's useful in kurtosis is we need to have a benchmark for what is normal. You know, what is, yeah, you need to have some kind of benchmark. So when we evaluate kurtosis, the benchmark that's most often used is the kurtosis of a normal distribution. So let's look at the kurtosis of a normal distribution. So if x is a general normal distribution, and you go and you do this integral, it turns out this thing is 3. Okay, so that's kind of nice. So the benchmark value of the kurtosis, that is the kurtosis value for a normal distribution, is 3. So if a random variable has a kurtosis that's bigger than 3, then you know that the distribution for that random variable has fatter tails than the normal distribution. That is, it implies more extreme values than the normal distribution does. Okay? Now, on the opposite side, what happens if the kurtosis is less than 3? If the kurtosis is less than 3, then you have thinner tails than the normal distribution. So you can think of 2 cases to consider. So if kurtosis, say this is my benchmark normal here, and then a distribution with fatter tails than the normal might look something like this. Okay, so here the kurtosis for x would be greater than 3 for the red distribution, because we have more probability in the tails than the normal distribution in that case. I'm not the greatest artist. Okay, so, and then the opposite case to consider, where's my colors? So again, here's my benchmark normal, and then this case, what if the distribution looks like this? So in this case, the distribution for x has thinner tails than the normal, so this red distribution would have a kurtosis that's less than 3. So now because the normal is the benchmark, then very often when kurtosis is reported, what's being reported is actually something called excess kurtosis. And excess kurtosis is the kurtosis of the random variable minus the kurtosis of a normal, which is 3. So if excess kurtosis is 0, then you have the same kurtosis as a normal. If excess kurtosis is positive, then you're in this case. And if excess kurtosis is negative, then you're in this case. So when we start looking at data, we'll actually do some probability calculations of extreme events based upon the normal distribution. And then we'll actually look at the likelihood of extreme events based upon the actual data. And that's another way that we'll see that the normal distribution is not a very good distribution for certain kinds of returns, because it doesn't imply that extreme values happen very often. So for example, if you look at like the crash in October 1987, so if you assume returns are normally distributed, the crash is an event that would happen, you know, once every 6 trillion years. And so essentially the likelihood of that happening is 0. But you know, it did happen. And whereas if we have other kinds of distributions that have thicker tails, then we would actually have you know, a reasonable probability of such an event like October 1987 happening. So from the point of view of risk modeling, and this is a thing that I want to emphasize as we go through the course, the distribution that you use for returns is incredibly important, because the distribution for returns tells you the likelihood of good or bad events. And if you're trying to characterize the risk associated with investments, then your distribution is paramount to giving you the information for how to make decisions. So getting the right distribution is an important thing to do, and we'll see that that's not always an easy thing to do in practice.